Good morning, Code Milkers. Welcome to Milk the Code. Today's problem is minimum path sum. I've already figured this one out. It's another one like yesterday's where I anticipated it would take me a while to figure it out, so I didn't bother recording it. I'm just going to show you my solution, explain it, and maybe it'll help you figure out your own solution. So, given a m times n grid, so that's an array with subarrays, filled with non-negative numbers. Find a path from the top left to the bottom right, which minimizes the sum of all numbers along its path. You can only move down or right at any point in time. That's key to understanding the problem. Move down or right, that's it. So we have here our input. We have an array with 3 subarrays. Notice that the length of each array within the array will be the same. Okay, so we start at 1, 3, 1, 1, 5, 1, 4, 2, 1. And now we have to find the path down to the bottom right, which has the minimum sum. So in this case, it's 1, 3, 1, and then 1, 1, which has the sum 7. So when you hear the idea of minimizing something, it's a good idea to use dynamic programming, where we break up the main problem into subproblems. And our subproblem here is going to be figuring out which path, either coming from the top or coming from the left, which one results in a smaller sum, and then we want to trace that path down to the bottom right. So with my solution, I'll give you a high-level overview of just what the iterations look like. So if we're going through the array, we start at 1, 3, and 1. Now, I instantiated a new array to keep track of the sums as we go through. So there's 3 subarrays, just like in the input, but instead of standing for the actual number in that index, it's going to be the minimum path up to and including that index in the original array. So it'll make sense in just a minute when I go through some of the iterations. So we're starting at 1. Now, since it's the first element in the first row, there's no top and there's nothing to the left, so we just insert it. 1. Next we go to 3, and since this is in the first row, there's nothing on top, so we have to move from the left to that one. So we add 1 plus 3 is 4. Next we have 1, and since it's in the first row, there's nothing above it, we just move from left, which gives us 5. So as you can see, the element in the index is the sum of the minimum path up to that point, and including that index. So I move down to the second array, and we're going to start with 1. Now, since this is the second row, and it's the first index of the second row, it means we can only come from above. So we have to move down from 1 to 1, which is a 2. Next we have 5, so it's either going to be 1 to 4 and then down, or 1 to 2 and to the right, which this one will be 1 to 2 to 5, because that's smaller. So 8 is smaller than 1 plus 4 plus 5, which is 10. Now we have a 1, so we can either go from the left, which is an 8, or we can come from the top, which is a 5. We're of course going to go with the top, which gives us 6. Now we're starting here with a 4. Since it's the first element in the row, we can only move from the top down. So 1 plus 2 plus 4 is 7. And next we have a 2, so we can either move from the left or from the top down. Now, since we're comparing 8 and 7, we want to take the minimum of those two, which is 7 plus 2 is 9. And now we're at the last element. So this is the element which determines the minimum path. Like, this is the indexed element which actually holds the answer we're going to return. So we hit 1, and we decide, is 6 less than 9? Yes, we add 6 plus 1 is 7. So 7 is our minimum path, and we return that 7. So basically the subproblem is comparing it to the left and the top, and it takes the minimum of that and it adds the current element to that minimum path and assigns that index in the new array. So let's look through the code for it. We start off with our new grid. Now this is the grid here, which I instantiated. It's just an empty array at first, and then for each row in the original grid, we're going to push a new array into it to hold the new minimum path values. Then for each element in a row, so kind of like the columns, we're going to go through each of them, incrementing by 1 each time. Now this if conditional, this big conditional statement, this is where the magic happens, so to say. So this first one, if I is greater than 0 and j is greater than 0, means that the element has a top and a left element. So we're looking at 5 and 1 and 2 and 1 here in the initial input. The next one here, I is greater than 0. That means we're just at a row in the array where it's greater than 0. So we're in one of these two rows. Now here, j is greater than 0, but I is not greater than 0. So this means that the only thing we're looking for is if j is greater than 0, which means we are in the first row. But our j is greater than, but we're not at the first element. We're beyond the first element. And then lastly, this else statement here covers the first element of the first row right here, because I is equal to 0 and j is equal to 0, and none of these conditionals cover that value. And here's where we're returning the last index of the last row in the new grid, which is our minimum path. And here, these statements in here, underneath each conditional, is where we are pushing the new minimum path to the current row. So the only one where we're assigning the min is in the case that we have 5 and 1 or 2 and 1, because we have to compare two values. Because in all the other if statements, there's only one option. So if j is greater than 0, we know we're in this row, so we have to move from the left, so we have to take that. But if I is greater than 0, we know that j is also not greater than 0, so we're in the first element of either of the last rows. So we have to move from top to bottom. So here's the logic for that. It gets a little wordy. In hindsight, I would probably rename I to row and j to column, just so I could be more clear on what I and j stand for. But the solution works well. Show you how fast it is. It's not that fast. It gets the job done, but I don't think it was that fast. Yeah, just 19% of JavaScript submissions are beat with it, so it can be optimized. I'm not sure how, but that's another problem for another day. Have a good day.